Oh, should we put that? Oh, for questions. Okay, so Janine, you'll have to stand close to the microphone so the online people can hear you. I think for online people, can you just indicate you can hear me? Just raise your head or wiggle your hand. Perfect. Okay, super. So welcome everybody to today's Geotalk. This is work Janine Cole has been working on for quite a while. And Janine is a scientist at the Council for Geoscience who's been there, gosh, I don't know, almost as long as I've been at Wits. Actually, probably longer. So she's been there quite a while, and she's also one of my graduate PhD students. So I'm very proud of a lot of the work she's done, and we continue to collaborate, especially on the Bushveld. And this new staging chambers work has been a long time coming. We've had a lot of arguments and discussions and just lots of fun doing the science on this. So I will turn it over to you, Janine. Thank you. And thank you very much for driving down from Pretoria and risking all the traffic. So we appreciate your in-person presence. Thanks.
Thank you. Can you hear me? Okay. Okay, thank you for the invitation. Just get the, I can't see the thing to do the pointer, but it's okay. So thank you for the invitation. So the talk is about, as Sue said, about modeling that we did that show potential magmatic staging chambers under the Bushveld Complex. With there's an echo somewhere. Okay, so okay, so last year about this time, Sue had a mini symposium, and I presented on this as well, but I tried to add some more stuff, and since then our paper has come out, and so hopefully there's some new things that you haven't seen, and I don't know if I'm actually in control of this. Can you just come and see? Because I can't see the thing. Oh, there's the pointer. Okay. Yeah. Okay. Yeah. Thank you. I didn't see it. Okay. So at the council, we always have to show this disclaimer, as to say that the information here belongs to the council or whatever, and you mustn't copy it or use it without written consent. And what I say is done. I took as much care as possible to do the best job I could, but if you use it and something happens, we are not liable. So, okay, so okay, okay. Okay, so I thought, where do we start? I mean, everybody here probably knows about staging chambers, but I'll start at the very beginning. So originally, there was the concept of you need a big magma reservoir where all kinds of geochemical things happen and magma mixing and things. And then from there, you can get either volcanoes or layered intrusions. But then more recently, people started to propose that you don't need a single big magma chamber or reservoir, but that you actually can have a series of chambers through the crust. That's why it's also called the transcrustal magmatic plumbing system. And you can have a mush column. We have lots of sort of more mushy material, and you have this melt moving up and collecting in sort of what's called magma lenses, maybe. And that can also explain much of the composition of layered intrusions. So this is just another picture. This one is for under continental arcs, I think, and this one is the model for under Iceland. So it can have, they've proposed different models, like you have this mush column with a magma chamber or magma lenses, and at different levels in the crust, different chemical reactions and things with it. surrounding rocks take place, or you can have a series of stacked sills, and in these sills also all kinds of things take place like fractionation and so on. What's interesting is that they note that these magma lenses can be ephemeral, so you don't always have remnants of them after an event. So where have these been proposed or imaged? Mostly at volcanoes, as you can imagine. So this is at Anak Krakatau. They did a they use seismic tomography data where you use seismic velocities. And if you take the ratio of VP over VS, the shear wave and the primary wave, then you can get an idea of the crustal composition. And under this volcano, they found like two possible separated magma reservoirs. The higher the ratio, the more mafic, in a simple way, the more mafic the crust is. And this was actually, this agreed with geobarometer models where they looked at where crystallization took place. And they found that you had plagioclase crystallization in up here, I think it's 4 to 8 kilometers or 4 to 6, and then at 10 to 12 or so, you had more clinopyroxene, and it coincided nicely with the limits of these reservoirs that were imaged by the seismic tomography. How they came up with the little chambers, I'm not sure. And then also at Hawaii, there they actually used seismic events because it's a very active area. So if you look at where all the seismic events happened, this is during the 2020, 2021 eruptions. They use that to interpret different aspects. I mean, here's a diagram to illustrate that. So at the bottom, you have long period earthquakes, and they interpreted that to be like a magma chamber or a melt area here. And then above it, we have more volcanotectonic earthquakes. You have a series of sills, which they call the Pahala Sill Complex. And the magma goes from this reservoir here up into the sills, and from there it moves along faults in the mantle. We're totally in the mantle here, and up to where it finally erupts. And you have two actually pathways. And apparently this was a big discovery for them, that these two different volcanoes at Kilauea and Mauna actually comes from the same source. So that is really a nice interpretation of seismic events. At mid-oceanic reaches, you have this thing called an axial magma lens. And they did this at the Juan de Fuca reach, where they did normal seismic surveys. And there they could image this or detect this axial magma lens, but then below it they found a bunch of reflectors that they interpreted as sub-AML lenses. And then you have the MOA here at the bottom, and then they interpret it as a stacked series of magma chambers in a sort of a mush area where you have lower melts at the bottom, and as you move up, you get a bigger melt percentage. And then also you can use electromagnetic methods. This is at Mount St. Helens, where an MT survey detected the conductive body in the lower crust, which they term the lower crustal conductor. And they also detected or mapped conductive areas going up around this batholith in pre-existing pathways. And they say that this was the source. This is like a staging chamber, and then the magmas move up from there. But it's not only at volcanoes and so on, but also at igneous complexes, although here it's mostly based on geochemical data, which I have to just also have my own disclaimer. I'm no geochemist. I'm a mere geophysicist, so geochemistry is like way above me. So if I make a mistake, just be kind. So, but in any case, I'll just give a very high level, sort of how I understand it. So at Stillwater, they used a staging chamber in the lower crust that has a chromatic melt in it. And they used whatever happened there, assimilation, batch crystallization, to explain the composition of the lower banded series. And then at Norilsk, they use it to explain how you get those huge deposits. So they use it to say, or they say this like, you've got your magmas coming in, and then you have sulfide-rich liquids that collect in certain magma chambers, and it scavenges, and the magmas then scavenge the nickel and copper and PGEs, whatever, from these staging chambers, and it gets deposited in trap sites, and that is why you get such good concentrations of these minerals. So you can see it has been used or invoked, I can say, in many different areas. So geophysical, there is definite geophysical evidence of staging chambers or transcrustal magma systems in active areas. You have seismic activity, you have hot areas where there's melts, which you can see on EM data, and you can see it on like changes in velocity. But the question is, what about ancient staging chambers where it's not active anymore? Is there any evidence for that, for magma chambers or staging chambers at depth there? And this is where our model comes in. Our hypothesis is that the modeling that we did using gravity data supported by the seismic receiver data from the seismic tomography studies actually show that there are possible staging chambers under the Bushveld complex. So it started when I did a forward model of the Bushveld complex. So here you put in your model with the forward model, and you calculate the response and compare it with your observed data and try to get the best fit. Unfortunately, there are not so many constraints that we have from other data. We have a few seismic reflection lines that can give us information about what's going on at depth. We have a few boreholes. And then we have the seismic receiver function data, and and then also a lot of petrophysical information, densities, and also use the magnetics. So that also helped to constrain the model. But what I found was, as I modeled, even with all these sort of constraints that we had, I couldn't fit the observed and the calculated if I didn't add additional dense material below the Bushveld complex. This is not just a DC shift. You need sort of, at that point it has to move up more. You can see this green line, sorry, shows what the response is if I don't have the deeper dense material. But if I add deeper dense material, then you can see there's a very good correlation between the observed and the calculated. And the same, these are just two profiles I took across here, and the same here. So this made us think that maybe these are remnants of staging chambers. You can also see in the south here, in this one on the south, there's like I had to model a feeder here to enable to model the gravity high. You can model a feeder here, and that, as well as the Dabazimbi Murchison lineament, coincided with these dense areas. So before I go into inversion modeling and results, just want to just emphasize that this was a very regional study. It's not detailed at all. We're not looking at small things happening on a small scale. It's sort of a conceptual model, and we're looking at large features. We also included the Malopa Farms complex and the Moshaneng complex here in Botswana because they have similar compositions and very similar ages to the Bushveld complex. And they form part of what people call the Bushveld province. Some people call it that. So, and then important for our study is these large east-northeast striking structures. The first is the Palala shear zone in the north that separates or sort of forms the boundary between the Limpopo mobile belt and the Kaapveld Craton. And you have some Bushveld cropping out there in the Villanora area. I think that has been reactivated over time as well. Then, of course, everybody knows the Dabazimbi Murchison lineament that probably carries on even further west, but it's a big zone of faulting, and it's been reactivated many times. and consists of relay structures and everything. And then in the south, we have two faults that may be less well known. The Sugar Bush fault, which is an old fault, but there's not a lot, there hasn't been a lot published about it. We don't know if it even goes, how deep it goes, but it has the same orientation as these other big structures that we know a lot more about. Then there's also the Nyoka fault. This is actually, it crops out in the, or you can see it in the Barberton Greenstone belt, and it's interpreted to be a suture zone between Archean blocks that made up the Carpfell Craton. So it's definitely a deep structure, but its locality is not well known. So whether it's part, it's also one of these east-northeast striking things, we're not sure. Other things we look at is then feeders. So the Tabazimbi Murchison lineament has been proposed as a feeder a lot over time. And in the forward modeling that I did for this part of the Bushveld, and my co-author Carol, she did the northern lobe, we both had to include quite dense material in this fault in order to fit the gravity and magnetic data. So, and we interpreted both that is actually material caught up in the fault as it moved up from deeper. There's of course the Mokopane feeder, which causes a huge gravity anomaly, 110 milligal anomaly. It sits on the sort of an intersection. You've got the east-west striking and north-south striking faults there. And even long ago, Maurits van der Merwe, I think he modeled first that there might be a feeder there. And it's really the only way you can model that anomaly is by a very deep sort of funnel type feature that's quite dense. So that is considered, I think it is definitely a feeder. And then in the south here, as I said, to fit the gravity data, you also need to extend the lower zone or whatever, the lower zone I did deeper, that makes it also look like a feeder. So this is the data that we used, the Bouguer anomaly gravity data showing the Bushveld complex. And here's you can see also it's denser over the Mulepoor Farms complex. And then the SASSI data, and it was supplemented by data from Botswana. So the SASSI data, everybody here is probably familiar with it, collected between 1997 and 1999. And on the Bushveld, we have 16 stations in and around the Bushveld. So only 16 stations. They're about 100 kilometers apart. And then more recently, between 2013 and 2018, a similar type of study was done in Botswana. I call it NARS, and for the life of me, I can never remember the N. It is some automated receiver seismographic station or something. But in any case, it's NARS. So they have a few stations that we can use that supplement our data in this northwestern area. They are a bit further apart, 150 to 200 kilometers apart. So for the Bushveld complex, the first thing, or when we first started working on it, quite a few crustal thickness models have been published by different authors using different methods. So we decided to actually just take an average because it's the easiest. You can't choose one above the other. So we took an average for the Bushveld, but for the Botswana stations, we only had one that we could use. And what we can see is the thicker crust under the Bushveld, and which of course was great news for Sue and Grant Cawthorne because they postulated that this is the case. And I think when this data became available, they must have had a nice party because it totally supported their hypothesis. What I can say also is that all the people who did crustal thickness models in this area using seismic receiver functions mentioned that it was very difficult, or the conversions from the P to S waves, which mark the contact between the crust and the mantle, was very diffuse, and it was very difficult to pinpoint it, it's quite diffuse. So that was a very important data set in our modeling. Then, as I also showed for that one example, we used if you look at the apparent VP over VS, which gives you an idea of the composition, you see that under most of the Bushveld complex, the values are quite high, which means it's more mafic. Also here at the Mulepo Farms complex at the top here, unfortunately, we need more, as a scientist, we always need more data, and it would be nice to have a few more stations here and here, just for that matter. But in any case, so, and this area of more mafic material coincides with a thicker crust. And then somebody calculated the Mohs sharpness, also using this data, and he found that under the Bushveld complex, the sharpness is it's not a very sharp Moho. So lower values mean it's not sharp, higher values means it's sharper. But unfortunately, we don't have that for Botswana. But this also coincides with the mafic material and the thicker crust. So what is this? What does this tell us? So we have weak P to S wave conversions under the Bushveld complex, which means we have a diffuse crust mantle transition. And this is probably due to lower velocity contrast between the lower crust and the upper mantle under the Bushveld complex. And people have interpreted in different ways. Some people say maybe the mafic lower crust or the lower crust was mafic throughout during that period. But other studies from different parts using the same data and other data that Ray worked on many years ago showed that the lower crust is more of a more felsic composition generally. So this is only restricted there, I mean, our study to the Bushveld complex area. A lot of people say it's mafic underplating. It's a very popular theory. We can't say if it is or not from the data, but we have other reasons to think it's not. And then, yeah, what else can it be? And this is where our models come in. So we did inversion modeling. And for inversion, you give it the data, give it some constraints, and you tell it, and it calculates a model for you. Okay, so, but yeah, you have to be careful, but in any case. So this is, you have a starter model. In the first starter model, we decided to see what happens if you don't have any dense material in the lower crust. It's sort of an end member. So this is the model with the constraints we used in the inversion. So the Rustenburg layered suite was made like 7 kilometers thick, but the bottom was left unconstrained. So it can move up and down as much as it wants, and try to get the best fit between the calculated and observed data. The contact between the mantle and the crust, that we got from the crustal thickness model, so that was fixed. And it was quite dense. The upper mantle below the Bushveld is quite dense. Due to that, people say there might have been the magnesium depletion, and then you have higher iron, which will make it more dense. So then if you run the inversion, you get, this is shows the thickness of the Rustenburg layered suite. And you can see it's actually quite ridiculous because most of the values are either sort of from 10, 12 kilometers to even greater than 20 kilometers. And that is definitely not the case. I extracted the profile across here just to show at the top there is 2 kilometers above sea level, and so you can see everything here is like 10 to 15 or even more kilometers for the Rustenburg layered suite, which we know it's not realistic. The errors are between -5 and 5 milligauss, which is not too bad, but that is one of the problems with potential field data. You can have different models that give you relatively good results, but not very good, well, not true results. So then for the second model, we included a dense lower crust. In this model, we constrained the Rustenburg layered suite thickness. So it can only go down to 10 kilometers, which is still conservative because we know it's probably 7 to 8 kilometers thick. And it was unconstrained where there's possible feeders. And then this lower crust was set at 24 kilometers and it was unconstrained. So this boundary can move up and down as much as it pleases. And you can use different densities. This is again a conservative one that this yielded the thinnest lower crust. If you look at shear wave velocities, you can use that to determine densities, and normally it's quite a bit higher. But in any case, if you make it any lower, then you will have a very thick lower crust. So this was our input model. And this is the results. On the left-hand side is the thickness of the Rustenburg layered suite, and this is much more realistic. You know, it's between 7 to 8 kilometers and thinner in places. Of course, this is a very simple model. We don't have the granites, the Laboa granite suite or anything in here. It's just a very simple conceptual model. So, but in any case, the results look quite feasible and realistic. If you look at the thickness of the lower crust, it shows the thickest or very thick crust here under this part of the complex where you have the Tabazimbi Murchison lineament, you have the thick crust, mafic material, and weak P2S conversions. And also under the Mokopane feeder, you have thick crust here for some reason under the far western lobe, very thick crust under the Molopo Farms complex, and also quite a thick crust here under the Sugar Bushveld, where we have another modeled feeder. The errors are smaller in this case, so that is good. If I look, I'm just going to struck some profiles, just a few profiles that we can see in more detail what we're looking at. So if we look at this profile over here, going from south to north, and I move this thing. Oh, okay. So this is the extent of the Bushveld complex here. Then you have this is sort of the extent of the Tabazimbi Murchison lineament here. Here you have the isostatic adjustment at the mantle, at the moa. So you have thicker crust, but you have thick lower crust here as well. You can see the model you'll see the Rustenburg layered suite sort of extends everywhere, but as I say, there's probably other rocks. It's not a detailed model, so we're just focusing on what's happening in the Bushveld complex. If we look now at this profile crossing this southern feeder, you can see there the inversion model also had a bit of thicker Rustenburg layered suite and also thicker crust, and up to here where you have the Tabazimbi Murchison lineament, where you have also slightly thicker crust. Going from east to west, this one crosses the Molopo Farms complex over here. There the crust is very thick. This is the far western lobe, and then this is the extent of the Rustenburg layered suite, and you can see thick crust under in this area under this lineament, and even that's just under the Steelport fault is not much thicker. And finally, one going through the Mokopane feeder. So the feeder is there. The model actually modeled it also as a feeder, the inversion model. Remember, we didn't control, we just said it can go, it's unconstrained, but it also came up with a sort of a funnel shaped model and a very thick lower crust right at the same locality. And this is where we propose that they may be even still connected, we don't know, but that you had magma moving up from this staging chamber up to feed the Bushveld complex. Now this is a very simplified model. We don't have enough resolution in our data and enough data to say what's happening in the middle crust. If there's remnants, the model can be, reality will obviously be more complicated, but as a simple model, this is our conceptual model. Okay, so is there a way to validate the results? So one of the papers or studies that were done on using the SASSI data was by Ulrich Kaswane, who's actually a colleague of mine, and he did a shear wave velocity study, and he found in the lower crust also higher velocities. And he interpreted that where the velocity, shear wave velocities are higher than or greater than 4 kilometers per second, you have this more maybe mafic lower crust. So what I did was at all the stations on the Bushveld, I just extracted the thickness of the crust that we had, or the depth to the top of the crust, and then compare it to the depth of where the velocities increased above 4 kilometers per second. So first, when I did that, it was sort of mixed results. But then, so this shows a 1-to-1 relationship, and I added 5 kilometers on either side because those are the uncertainties in the crustal thickness models, and our data resolution was also, our model resolution was also quite big. But then if you look at these results here, they're also just models. So they also have uncertainties inherent in them. And he in the paper mentioned they can have uncertainties of 0.1 to 0.2 kilometers per second. So then if you look at where maybe the velocities are above 3.9 kilometers per second, and you plot it against our results, there's actually quite a good agreement, although there's not a lot of data, but most of them fall within 5 kilometers of each other. Okay, so just to summarize, so the model shows we definitely have dense lower crustal material, and we need that to model the observed gravity data, whether it's forward modeling or inversion. Where the crust is the thickest, this lower crustal material is also the thickest. It's also thickest where you have more mafic crust and where you have diffuse crust mantle transitions. It also is present under those large structures, east-northeast striking structures, and under the feeders that we have modeled for the Bushveld complex. So there's definitely a connection between the dense material in the lower crust and the Bushveld complex. So the question is does that mean that the lower crust dense material is a staging chamber? And from the geophysics, we can say there's dense material, but that is about it for now with the data that we have. But if we look at the literature, staging chambers have been proposed quite a while to explain certain complexities and compositional variations in the Bushveld complex. So once again, disclaimer, I'm not a geochemist. So even in 2009, Naldred and them, they saw that in the Western Bushveld, if you go across the Marinsky Reef from the bottom to up to above it, there's a decrease in the platinum tenor and an increase in copper palladium ratio. And they proposed that what you had was staging chambers where again sulfide rich liquids, and then as the magmas move through it, the chalcophile elements in the PGEs were scavenged from that, and at some point it was deposited in the main sort of Marinsky Reef. And while it was deposited, there was still some fractionation happening. So as you move up, you get less and less platinum, and also as you move away from the feeders, that happens. Okay, so that's how they explained it. And then Lou and Freddie Rulofse, they saw there's some isotopically heterogeneous plagioclase in the lower main zone of the Bushveld complex. And then the way they explained it was if you model it as a compartmentalized sort of staging chamber in the lower crust, part of one is more situated in the upper crust and one more in the lower crust. And they actually used data from the Frederick dome where you have a nice cross section to model what would happen if you have crustal contamination from the lower crust and from the upper crust, and that explained their what they observed in the data. But I think in the let me not say it, I'll get it wrong, and he's sitting here. So they also say that these matched columns explain the lack of layering in the main zone. Then there's the chromium paradox that everybody probably knows about, that you have the amount of chromite that you have in the Bushveld complex cannot be explained by the proposed magma, parental magmas that you have. And so they, Eels and Costin proposed that you had like a chromium-rich chromatic melt, and in a staging chamber below the Bushveld complex, and through gravity, the chromium was collected at the bottom. It settled there, but as subsequent magma was in place, it was carried up and into the Rustenburg Lakes, where it was deposited. Very high level overview. And then there's also something called but McDonald and them in the paper called the PGE paradox in the northern lobe, where they see these very, very high platinum tenors or PGE tenors in the Platte Reef. And they say that the Platte Reef was intruded as a series of sills in the Transvaal and lower Transvaal rocks. And it was actually solidified before the magma for the lower main zone intruded, and therefore the lower main zone magma could not be the cause or for this high platinum group elements or high concentrations of it. So they proposed that you had again a sulfide rich a staging chamber with sulfide rich liquids that once again scavenged nickel, copper, and PGEs out of the magma as it passed through it to form the lower zone, which is just here. It's not continuous in the northern lobe. And then at a later stage, you had a new magma coming through, and it sort of took all these in nickel, copper, and PGEs up and deposited in the Platte Reef. And then finally, you have thermodynamic modeling, which basically says that you don't need a big magma reservoir to explain the compositional changes, but that you can have different magmas forming in different parts of the crust, different types of processes happening, and that can still explain the compositional changes and in the layer intrusion. And it also can cause layers to be out of order, so that the ages it's not like we think the lower zone, then the main zone, and so on. That's of course very controversial and has caused, I think, lots of arguments, but that's not for me to get involved in. All I'm interested is that staging chambers can explain what we see at the moment in the Bushveld complex. So if we put everything together, from the gravity modeling, we see definitely a link between the lower crust and the thick, dense lower crustal material and these large east-northeast striking features, the feeders, and so on. There's also a lot of geochemical evidence that it explains many of the observations in the Bushveld complex. And the thermodynamic modeling that shows that you can have that a magmatic plumbing system throughout the crust can explain what we see in the Bushveld complex. If we combine that with present day examples that shows there's a link between active staging chambers and structures, and that many of these melt regions have actually been imaged by geophysics. If we chuck all of these things into a pot, we come out with our conclusion that we believe that dense lower crustal material is actually remnants or a staging chamber or remnants of a staging chamber. Thank you.
We have a question from the in present audience in room. Sorry, go ahead, Ray. Or actually, let me. Room. Yeah. Hello.
Thanks, Janine. That's a really nice talk there. I want to just ask you a little bit about firstly your gravity data. I mean, you show these lovely contour maps. What is the density of your gravity stations? Are they equally spaced? Perhaps you could how many gravity stations have you got?
I can't remember the exact amount, but the data that we collected at the council is spaced at about It varies, it's not constant, but roughly one station every between 12 to 14 square kilometers. So it's very regional. Botswana, I think, was a bit better. I think it was one station every 7 square kilometers. It was then gridded up. Our local data is at 1 kilometer, but the data I used here, I got from the SADC data set, and that's gridded up at 2 kilometers. And it was done with old, Lacoste Romberg and heights from barometers.
Good. And when last was there a gravity collection campaign? There's been.
No, it's really something happening at the moment, other than small surveys in localized areas, just for, I don't know how much gravity they actually do for dolomites and so on, but there's not a big push to fill in the gaps in between the stations. But I can say, which I actually wanted to say, I forgot, is that one thing that would be nice is to have empty data. And although the Bushveld is there's a lot of noise from railway lines and so on, the council is actually in the process of trying to cover the whole country with empty surveys, as you probably know. And I asked Menentley, who's sort of running with this, he said probably not before 2 years from now will they get to the Bushveld, because we don't have that many people and that many systems, but I will eagerly await that. Because that maybe, I don't know, hopefully they can find a way to deal with the noise and, or in places at least see something.
And then just to follow up the inversion model, and maybe Patrick would know, you'll know for sure. How's that discretized? What was your cell size? Are these like prisms that grow or shrink?
It was actually the Voxy software, and the voxels were 5 by 5 kilometers.
Thank you very much. I'm just wondering how sensitive is the model, the calculation of how thick the mafic lower crust is on the thickness of the Rustenburg layered suite? Because you're using an average thickness of 7 kilometers, but of course it's much more variable laterally.
It will affect it, but at that great depth, I don't know. I don't think it will make like huge amount of. I think the density of the lower crust will make a bigger. You can correct me if I'm wrong, but I think the density will play a bigger role. I don't think we will have enough. The variation in the Rustenburg layered suite is big enough to cause big changes.
Because, like, where you're finding the thickest mafic lower crust is where you're getting the thickest parts of the lower zone at the base of the Rustenburg layered suite as well. So I'm just wondering if, it makes sense to me. But
I'm just getting to Grant first, and then Nick, I see your hand online.
Okay. Thanks, Janine. That was great. I was just wondering, maybe I missed it. Do you see connection between the feeder zones and the actual complex itself? Is it a continuous body, or is it a discrete body at depth?
You can see, sorry. Okay, so here, for example, at the Mokopane feeder, this model doesn't show it to be connected, but as we say, it's a very simple model. It is possible that they are still connected. We just, you can probably model it that way. But this is definitely, you've got a really thick, there's probably some trade-off between, I don't know, if you make this much thicker, then this will become a little bit less. But in terms of whether they're connected, I can't really say from the data, but they're co-located.
Okay, and Nick Arndt, I saw you had your hand up earlier. Do you want to unmute?
I'm unmuted now. Can you hear me? Is it okay?
Yes, we can hear you.
Okay, Janine, a nice talk. I'm afraid I'm going to ask some questions about petrology, geochemistry, but it fits in with what you said. First, a while ago with Wolfmeyer, we published a paper using strontium and neodymium isotope data, which seemed to show that the magmas that fed into the Bushveld had been contaminated with material from the lower crust. So that basically fits your ideas. What I'm wondering, though, is what is this material now that you're imaging? You said that the VS values are around 4 kilometers a second. Is that right? Or higher?
Yes, yeah, 4 and higher.
4 and higher. Okay, because you talked about mafic material, and what I think is that if you take into account the composition of the main zone and the upper zone, these are relatively evolved magmas, which probably crystallized a lot of olivine and pyroxene, which was probably left as cumulates in the lower part of the crust. So I'm wondering, when you say mafic material, that's probably okay, but it was probably ultramafic, which would suggest rather higher velocities. Is that possible? Metrological model saying that the material you're imaging was probably mafic or ultramafic cumulates.
Yeah,
Yeah.
no, definitely. I don't think it's a problem to say it's probably just a misnomer from my side. I can't say if it's mafic or ultramafic, but I can't see why it can't be ultramafic. Ultramafic
Okay, I
material is
think that's
definitely
probably.
dense. Yeah.
Yep. Okay, thank you.
Okay.
Scott?
Yeah, thanks. That was a great talk. Just in the models that you showed, I mean, they're cartoon models, right? But I guess the feeder chambers are somewhat limited extent, or I suppose they're the same size as the eventual chamber in the upper crust. So I was just wondering, here you're mostly modeling just a dense layer across the entirety of the Bushveld area, but I suppose in a way that's just consistent with the models that you showed, or
Result, it's just an oversimplification, because when I did forward modeling, they were more separate. So then you have a bit more control. And I used higher densities as well. So, this is one model, but you can probably model it as separate.
and just one quick thing to follow up is, like, in a few of, I mean, of course, this is a model, and I'm not trying to interrogate every little anomaly on the map, but some of your maps seem to show, higher VPVS ratios, or maybe a broader extent of the Bushveld complex than, like, to me, it seemed a little bit north of the Palala shear zone, or I guess, to what degree do we interrogate to what degree do we interrogate those things? Like, is that interesting, or you're not that excited about it?
No, I think you have to. It can be. Well, we didn't focus on it, but it is interesting. I mean, you have the Limpopo mobile belt there to the north, so that's quite a. There was a lot of metamorphism and things. So I imagine, I don't know, some of it can probably explain that, but we didn't really focus on that so much.
Okay, and I see we have another question online. Kitso, do you want to unmute yourself, please, and ask your question?
Yeah, thanks, Susan. Thanks, Janine, for the nice talk. I just wanted to ask on the models that you're displaying now. I see that you've put the density for the upper crust at 3,000 kilograms per meter cubed. Isn't that a bit too high for the upper crust? What informed your decision for that value? Thanks.
Oh no, sorry, that's probably I should have said the Rustenburg Lake Suite. That's for the Bushveld. Sorry, that is not. It's not supposedly the whole upper crust. It's just the Bushveld. It's the Bushveld layered the Rustenburg Lake Suite. That's dense. So we took sort of. It varies over the thing, but that's sort of an average. It's just showing that it's denser than the surrounding crust.
Okay, so like in profile 4, for example, that green color shouldn't extend all the way from that distance of 0 to, say, 400 kilometers?
Well, you have the Malopo farms. Well, let me see. 4 is here. Yeah, no. There's probably other types of. It's probably dense material there. Don't know how thick it really is there, but it's or somewhere in the crust, maybe not at the top, but it's just the result of the constraints on the model, because we didn't want it to go deeper than a certain depth. But these are just sort of a result of the way of the inversion modeling, where you don't really constrain it that much. I don't know if it makes sense. I don't know how to explain it.
It's all right, thanks. One last question, Janine. The modeling software you used for the inversions, what is it called again? Thank you.
It's Geosoft Oasis Montage, and they have a Voxy. I
Okay.
think they call it Voxy.
Okay, thanks very much.
Okay, and I see we have another question online. Labakong, do you want to unmute yourself and ask your question? We can't hear you. Can you unmute?
Can you hear me now?
Yes, we can. Thank you.
Sorry about that. Thanks, Sue. Thanks, Janine, for the great talk. Just a question. I think it's all sort of touched on it. With the modeling in Voxy, I just have a question. Did you model the whole of the Bushveld when you did this, and the sections we're seeing are like exported voxel sections from there?
That was this whole area. This whole area was modeled, but actually extended further south. But we're only interested in this.
Yeah.
Bit, yeah. And then then you get the upper and lower surfaces that were exported, and then that is basically what I show here.
Okay. Thanks.
Oh, great question. Okay, do we have any other questions online? I don't see any other hands up. And any more in the room? Okay, well, let's give Janine another round. Thank you so much. Thanks so much for coming through. And once again, thanks to John Hancock's and CCIC Cole. I always get that wrong. And I guess we're on to the next one, which is the next speaker. Putting you on the spot, Robin. I'd also like to thank Robin for organizing the advertising and sending things out. And it looks very professional now with our new layout and everything. It looks really great. Okay, so there'll be a group talk next week and we will look forward to the advertisement. Okay, thanks everybody. Bye.